Hello, everyone. I'm Mengjiao Xiao, a postdoc at MIT. Thank you for having me here to report our recent work. I actually worked on an underground project for the dark matter direct detection before, but today I'm going to tell you something about the astrophysics, the constraints on Axion-like particles from a hard X-ray observation of Betelgeuse. First, I would give a very brief introduction to axions or axion-like particles. As well known, axions was proposed to solve the strong CP problem in QCD about 40 years ago. Axion-like particles were more generically predicted by many extensions of the standard model, such as the string theory. Besides, as the solution to a strong CP problem, axion or axion-like particle also presents an excellent dark matter candidate. If Fa here is very large, the axion will have a very weakening coupled field, and the vacuum expectation value evolves towards zero from its initial conditions in the early universe. Then the axion has the exact properties of cold dark matter and solves the dark matter problem for free. Theoretically, axions or axion-like particles may couple to many standard model particles, such as gluons, quarks, and photons. A lot of experiments over the world are performed to search for axions or axion-like particles using different technologies and from different views. Today, I'm focused on its coupling to the photons, which is permission for detection. This plot shows the current constraints on the axion-photon coupling. Here, axis is the axion mass, and the y-axis is the coupling parameter, J gamma. So there is significantly unexplored parameter space. Your experimental efforts are growing fast. In particular, I would emphasize your unique role of astrophysical observations to probe your low mass region. Here is a simple cartoon to demonstrate the working principle of axion searches with astrophysical observations. We usually use massive stars as the axion factories. Theoretically, within some extreme environments, for example, in your cores of stars, photons can convert into axions, well, such as the Markov process. These produced axions could escape from stars and travel in the universe. On encountering the galactic magnetic field, we have a chance to reconvert back to photons and then be detected by your space telescope. Why did we choose Betelgeuse? Betelgeuse is a red supergiant in the constellation of Orion. It is ideal for axion searches. First, Betelgeuse has been well studied. We know well about its luminosity, temperature, and the mass. All this indicate Betelgeuse has a hot core and would be in advanced stage. Thus, Betelgeuse would be a copious axion producer. Second, it is nearby at a distance around 200 parsecs. Actually, Betelgeuse is one of the nearest stars to the Earth. In addition, Betelgeuse doesn't have the solar-like corolla, which would emit X-rays always, and there are also no bright sources around. So there is no significantly streamlined contamination in this range. These facts essentially provide zero standard astrophysical background. Next, there existed other X-ray observations from Chandra, which is useful for the cross-check. We are interested in the Markov process in this work, so the axon production rate from Betelgeuse can be numerically calculated with this formula. These parameters are determined by the standard model. Here, we use the TCC, the time until the core collapse for Betelgeuse to model its standard stage. Then fitted each standard model to extract their parameter values. In addition, practically, the axon-photon conversion probability in an external magnetic field can be calculated with this. Here, we assume a homogeneous regular B field, and the BT value is in the range of 0.4 to 3 microgauss. Combine the axon production rate and axon photon conversion probability. Now we can predict the axon photon flux. It is proportional to 2 power of BT and 4 power of J gamma. This plot shows the expected event counts from Betelgeuse for each standard model. Here we assume the BT at 1.4 microgauss and the J gamma at 1.5 times 10 to minus 11 per GeV. So if we are focused on the low mass region, say the mass below 10 to minus 10 eV, their photons mainly fall in the hard X-ray energy range. In our study, we used the NuSTAR satellite telescope for Betelgeuse observation. NuSTAR stands for Nuclear Spectroscopic Telescope Array. It was launched in 2012. NuSTAR instrument has 2 identical co-aligned telescopes. Each consists of an independent optic and focal plane detector, referred as FPMA and FPMB. Each telescope subtends a field of view of about 13 by 13 arcomillets, with a half-power diameter of around 60 arcoseconds for point source near the optical axis. More technical details can be found in this paper. This plot compares the energy range for various X-ray telescopes. So NuSTAR is the best existing instrument to detect the hard X-rays in your space. Now, after counting the NuSTAR instrument response, the expected axon photon flux from Betelgeuse is shown here. Each line, again, is for one standard model. We will come back to this later. The instrumental response files were extracted from the south region of Betelgeuse observation. With the NuSTAR telescope, we had the first hard X-ray observation of Betelgeuse in 2019 August. The total duration was around 50,000 seconds. This picture is the observation imaging from FPMA in a full energy range of 3 to 79 keV. We choose the region of radius 60 arcoseconds around the star's equatorial coordinates as the south region, as the white circle shown here. To model the background, we extracted the background region in the green one. The background region selection protocol is following. It should be on the same detector chip as the source region. So in that case, we can properly describe any spatially varying backgrounds. It might be hard to see here. There are actually 4 detector chips on each focal plane detector. Then we required the background region separated from the source center by at least 120 arcoseconds. In addition, we observed a point source near the edge of both FPMA and FPMB. This source was not detected above 10 keV, but to be conservative, we choose the background region at least 60 arcoseconds from this object. Your standard new star data reduction pipeline was used to process the data. For the source region, your instrument response files were extracted simultaneously. As mentioned earlier, these files were used to calculate the predicted Axion photon flux. To count their expected backgrounds, we normalize their background spectrum to the source region. Your left plot shows the data from FPMA, which is binned by 1 keV for presentation. Your right line here is the source spectrum. Gray and the blue is the background spectrum before and after region size normalization. The residual spectrum after the background subtraction is on your bottom. Your event counts fluctuate around 0 within your statistic uncertainty. This table summarizes the event counts for the observation and the expected background. No excess above the background was found. To interpret the data, we performed the profile likelihood analysis for data fitting. So for FPMA and FPMB, the ambient likelihood function was constructed like this. Here, NAX is the predict Axion counts and NBKG is the expected background counts with their PDF respectively. In our analysis, the signal PDF was derived from their simulation. For each combination of BT and TCC, we have their unique PDF as examples shown here. Your background PDF was data-driven. As mentioned earlier, we derived their background spectrum from their background region. This data were used to build their background PDF. FPMA and FPMB are two independent instruments. So we combine their two data sets to extract their final limits. Here are our final results overlaid the ones from other experiments. The region labeled in red and above is excluded by this work. The width of the net red band reflects the uncertainty due to the choice of stellar model and magnetic field. As listed here, we use the conservative BT and modeled their Betelgeuse evolution in a very large time scale. So with the hard X-ray observation of Betelgeuse, we set a new competitive bound to the Axion photon coupling in low mass region, which is around 3 times stronger than your CAST experiment. This plot compares our results to other astrophysical constraints in the low mass region. Our most conservative limit exists the bounds from extragalactic supernovae, and the most stringent limit is comparable to that derived from the long observation of gamma rays from supernova 1987A. There are stronger limits derived from the lack of spectral variation observed by Chandra in NGC 1275 and in a report of M87. One point we want to bring up here is each astrophysical constraint has its own unique sources of systematic errors. But the combination of variation astrophysical constraints builds the confidence in the robustness of the equation at this mass corner. Finally, there would be one more benefit from our study. We derived the G-gamma evolution as their stellar models of Betelgeuse. So if future low mass Axion experiments discover axions, we can come back to our original assumptions and set a lower limit on the remaining time until your core collapse for Betelgeuse. Okay, that's it from me. Thank you for your attention.